Hello and welcome back for another VMK in the game development series. In this VMK, I'll be showing you how to create a flat grid object. And we're going to be needing this object so that you can get a full appreciation of how lights work in OpenGL. The lights that we'll be using are vertex-based, not pixel-based, which means you need geometry that has a good number of vertices in it, or else the lighting calculations will really not look very good. So if we have a flat surface, if we just represent that as one big quad or two big triangles, and then you place a light over top of this object, you won't really be able to see a nice gradient shading over top of this flat surface. So instead what you need to do is you have to add more vertices to this flat surface. For instance, make it a grid with maybe 10 by 10 vertices. And by doing this, then the lighting calculation in OpenGL will be able to get the lighting for that entire surface more correctly. So if you find my videos helpful and you'd like to support my website, you can go to www.maticnose.com and click on any of the Google's ads found on the right hand side. You can also support my website by clicking on the PayPal icon. Now, in our game engine, before we go and create this new .cpp file and .h file, I want to go into Paint Shop Pro and sort of give you an explanation of how this grid is going to work. So you'll be able to define a grid that's of any width and of any depth. Now I'm saying depth for the height here on the screen because this grid is going to be represented in the 3D world horizontally, meaning it has no elevation, nothing along the y-axis. It's only going to be represented in the x-axis and the z-axis. So the x-axis is going to represent the width, and the z-axis this way is going to represent the depth. Now in this drawing that I've shown you here, I've set it up so that these yellow spheres represent the vertices, and the lines represent the shapes that comprise this entire grid. Now you're not really going to see these little triangles because everything's going to be rendered smooth, so you won't see them. But this is the way that the grid itself is made up. Now the width of the grid is the full width from the one edge down to the other edge. This is the full width, and the full depth is again the full length here. In this drawing that you see in front of you, I've divided the width into 6 sections, and you can see there's 1, 2, 3, 4, 5, 6 columns, and the depth itself has 8 rows. This is important because the larger these numbers are, the more resolution you're giving into your grid. So you can have, for instance, a grid that's 100 wide and 100 deep, but you can change how many divisions there are. So you can make it one division, which will mean you just have 4 vertices, one here, one here, one here, one here. Or you can give extra divisions, and then you'll be putting more vertices inside the grid. We'll be playing around with this once we actually implement the light class in our game engine. But this is the structure that we'll be using, and notice the way that each of the triangles is oriented. We sort of have a triangle that's oriented with the diagonal always pointing in the same direction for the entire grid. This is important because the way we're going to be rendering it, we're going to be not using triangles. Instead, we're going to be using triangle strips. And I'll talk about triangle strips in a little bit once I go and explain the code. But the whole idea is when we go and render this, we're going to be rendering one of these strips, so one row at a time. So we'll render this row, we'll render the next row, and we'll render the next one, and so on. The way that the rendering works, the triangles need to be oriented in this way for our code to work properly. Now, I'm going to be using a one-dimensional array to store every single vertex in memory, and the array itself is going to be defined in the following order. So we're going to start in the top left-hand corner here, and that's going to be vertex 0. And then we're going to work our way across, incrementing by 1 for every vertex. So this is 0, this is 1, this is 2, and so on. And then once we get to the very end, then the next vertex is going to be the one below it on the very left side, and then work it way across again. And again, keep this in mind. Maybe get a printout of this screen here so that when you take a look at the code, you can understand why we're ordering our vertices in the way that we are. And they have to be done in a specific way, or else when you go and render, you may be rendering the triangles in the wrong order, or things will not render correctly. So make sure you understand the numbers here. Now the other thing is, when we do render triangle strips, it's very important to notice these arrows here. We're going to be rendering the triangles as strips, which means the vertices that we define for OpenGL is going to go like this. It's going to take the first value, which is going to be here, the next value, which is the one below it, and then the following value on the diagonal. By defining those three in that order, we're giving counterclockwise rotation like this, just as shown in this little diagram here with the arrows. So this triangle is then facing in the correct direction. If we order these vertices in a different way, then we might get a reverse rotation, which means that the lighting calculation would be wrong and it may not actually render properly on the screen. So we need to have counterclockwise rotation. Now, for the next triangle, though, we're going to be representing it by taking this vertex, and then this new vertex. So here we have a clockwise rotation. So it's going to go counterclockwise, clockwise, counterclockwise, clockwise. Now the key thing here to remember is that every single triangle that we're going to be rendering is comprised of two vertices plus a new one. So you'll notice the first triangle, let's say this is the first one, we're going to take 0, 7, and 1. The next triangle, which is this one, is going to be 7, 1, and 8. The next one is 1, 8, 2, and then 8, 2, 9. So you notice that there's this pattern. This pattern is very important because when we write the code, we can simplify how we program it so that we minimize the number of vertices we have to send to OpenGL. Minimizing means we can actually speed up the game as much as possible. So that's the ordering of our triangles, and that's the way that everything looks. Last thing I wanted to say is our overall grid itself is going to be centered about the center point. So when we give it a width, let's say we give it a width of 100, when we go and render it, the center of the grid is going to be here, so we're actually going to be rendering a minus 50 this way and plus 50 this way to give the 100 width. So you'll notice we'll be using minus width divided by 2 and plus width divided by 2 for the x coordinate, and minus depth divided by 2 and plus depth divided by 2 for the depth, which is the z coordinate. And again, x is horizontally positive, z is towards us positive. Okay, so that's the structure we're going to be using for our grid. Now let's go into Visual Studio and start programming it. First thing we need to do is create a blank CPP and blank .h file. Let's go into the Solution Explorer here, and we'll be adding the new grid into our object library. So select Object Library, right click, and go Add New Item. And we want to create a CPP file, and it's already selected us here for the object library directory. That's good. And I'll call it flat grid. Click OK, and repeat this for the .h file as well. Okay, let's start with the .h file. We include at the top the core as well as color OpenGL and vertex 3.h. We'll need all these to be able to render and use this class properly. The flat grid class has a constructor which takes in the width, the depth, the division in the x direction, the division in the z direction, the color, and the graphics renderer. Virtual destructor, and then a Boolean render function here. The member variables is going to be a pointer to a vertex structure, and this is going to be holding all those vertices for our entire grid. We have a member variable for the color, one for the graphics renderer we're using, and then some internal values for the width, the depth, the number of divisions in both the X and the Z direction. And that's it. So let's save that and then go into the .cpp file. Okay, so at the top we include the standard precompiled headers as well as flatgrid.h. Then we have our constructor. And again, in our constructor we're passing our width, depth, number of divisions for X and Z, the color, and the renderer. And we initialize our pointer to be null because initially we haven't defined our pointer. We then save the render type that was passed into our constructor into our member variable, and we tune the following parameters. So if the user passes in here some values that are invalid, we just automatically convert them to be valid. So if the width is less than 0, then we automatically make it 1. If the depth is less than 0, we make it 1, and same thing for divisions. And then here we store the color, the depth, the width, the divisions for both the X and Z direction into our member variables. Now, the action happens down here. So the first thing we need to do is allocate some new memory for all of the vertices that this specific grid will need. And the way we figure that out is by taking the number of divisions in the X direction, adding 1 to it, and multiplying that value by the number of divisions in Z plus 1. And the multiplication of this gives us the total number of vertices that we need. So if we go back here and let's just take a look at that. So for instance, in our case, let's see here, we had a specific width and then we had 6 divisions. Well, in the X direction, if we count, we need 1, 2, 3, 4, 5, 6, 7 vertices to have 6 divisions. So we take 7 and we multiply by 8 plus 1 because we have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices this way. So 9 times 7 is the total number of vertices we need to contain this grid. So that gives us a new pointer to all that memory. If this returns true, then that means that we did have enough memory and everything's okay. If it returns false, then that means that this is actually null, which means that the operating system wasn't able to allocate enough memory for us. So we need to handle that later on if that's an error message. Then what we do is we go into a double for loop. And this double for loop basically will step through every single vertex in that grid and give it a value. So it's going to position it somewhere in space. So on the outside we're going to be going along the sort of rows of our grid, so in the Z direction, and then in the inner for loop here we're going to be traveling sort of along the X direction, so it's going to represent all of our columns. And the range of it is going to be division Z plus 1 as well as division X plus 1, same as we had up here because we need to account for every single vertex. And let's see what we do. Well, for every single vertex, the Y coordinate we set to 0, which means that our entire grid is going to be completely flat. If we wanted to have some sort of elevations and things like that, then we'd have to play around with this parameter. But for now, we're just going to leave everything to be 0, so it's going to be a flat grid. The X and the Z coordinates, we need to define where those are for every single vertex. The X coordinate we define as the following. We start at minus width divided by 2. So if we go back into our diagram, remember our center point is here, so we're going to start at minus width divided by 2. So we're going to be somewhere along this edge. And if we look here for the Z coordinate, we're going to start at minus depth divided by 2. So in other words, our very first value, our very first vertex is this one over here, because this is where we're starting from. Then what we do is for every single X value, we multiply the x value by f width divided by the number of divisions. So in other words, we're going to be starting here, and then x is going to be 0. So if we see here, it starts at 0, and then it increments by 1 every time. So we start here, and then we're going to increment by 1, which means that calculation is going to move this specific distance, because we're taking this entire width and we divide it by the divisions. So we're getting this length and we're adding it to it. So we get this one next, and then we'll get this one next, and so on. So we're going to be moving across horizontally. And then for the z value, we do basically the exact same thing, but we're using the z coordinate here to figure out how far we move each division this way. And then the key item here that we need to realize is this formula here. X plus z times I division x plus 1. What this does, it allows us to define our grid, our two-dimensional grid, as a one-dimensional array. So if we decompose this, we see I division x plus 1 represents the number of items in one complete row. So it represents how many of these are going to be in one row here. So for us, it's going to be 7, because we have 7 items. Then we multiply that by z, which means this entire value represents where we are located in our one-dimensional array according to sort of the row number. And then we add x to it, which means how far are we in the x direction. So for instance, if we were here, then this means that z would be 0, 1, 2, 3. Z would be 3. So we take 3 times however many rows we had. So we had 3 times 7. And then we have to add, this would be x equals 0, x equals 1, x equals 2. So this would be x equals 2, and z equals, what did I say, 0, 1, 2, 3 would give us this coordinate here. And all the math calculates exactly where in 3D space this item is relative to 0, 0, which is in the middle. So that's a little bit of math, but it basically puts all of our vertices in 3D space according to the divisions that we've specified, the width and the depth. The next thing is our destructor, and in our destructor, if we have allocated memory, so if this succeeded up here, then we have to make sure we delete the memory, or else we'll have a memory leak, so that's what that does. And then we have our render function. So in our render function, we have our common switch statement, which selects which render we're using. When we're using OpenGL, we first set the color of our object, so it's going to take the red, green, and blue value. We're setting the normal here to be upward, so in the y direction straight up. You haven't seen me use normal yet because we haven't done anything with lighting, but this is going to play an important role in the following tutorials. So just don't worry about this too much right now. And then what we do is we go into another double for loop here. And what this double for loop does is it goes through every single vertex and makes sure we order it properly so that we can render our triangle strips. And as I mentioned earlier, the way it does this is it's going to go through and it's going to select this one, then it's going to select this one, select this one, select this one, select this one, and so on. So as it's selecting those, it's inside this for loop. This outer for loop basically moves our pointer from this row down to this row, down to this row, and so on. So we make sure we get every single row of these triangle strips rendered for us. So that's the way that works, and then once that's done, it just breaks out and finishes. So we have that implemented. Now let's go add it into our class and see whether it works. So to do that, we should compile this, make sure I didn't make any mistakes. Okay, that's okay. Let's go into the game engine. Or no, I moved it now. It's in the scene. And under initialize, let's initialize a pointer to that flat grid. In a .h file, we'll need to include flatgrid.h, and I'm going to replace triangle here with flat grid, since we're no longer going to be using that gigantic triangle to represent our ground. Instead, we'll be using this flat grid. And inside the initialize, this is all okay up here. So here's the. So now we can go and do this flat grid, and we now have to specify a width. So let me think. Let's try using the following values. 10 for the width. Let me bring this up for you to see. So 10 for the width, 15 for the depth. We're going to have 20 divisions in the x directions, 30 divisions in the y direction. Then we specify the color that we want the item to be, the grid to be, and then our renderer down here. And then we do an error check. And I think that's all we need to change. Let's save this and try to build it. Okay, and then let's go run. Alright, and now you can see we have a nice square grid here where all of our objects are sort of sitting on top of. So we can play around with this. You won't see any difference now because we're not using any lighting, but once we implement the lights and start playing around with these settings here, then you'll actually see why it's important to have a dense grid. So let's just change this to be 1 by 1 for now, since it makes no difference. And let's make this 10, just so I can show something else for you. Okay, notice now I've made my flat grid not very long, so it actually looks like those houses up ahead are floating. But in reality, they're not floating. If we move up here, you see they're off of our grid. Our grid doesn't go nearly that far, but they're still, they would be rendered on the grid if the grid happened to go that far. But that's a little optical trick which makes the houses look like they're levitating, but they're really not. They're actually on the same level as the grid, but the grid just doesn't go very far. So that's just one other thing to remember when working in 3D. I'm going to get rid of this triangle window here because it's kind of distracting. Let me just, actually, the fastest way to do that would be under the render, just disable, under render here, disable the render, so we won't render that triangle on the screen. Okay, so no more triangle. Okay, that's it for this tutorial. Come back for the next one where I'll be adding the class for the lights, which we'll be implementing next.